So hi guys, we're going to talk about lab 1 of course ECE 360, and in lab 1 it says that pick 4 resistors at random and try to make a ratio of 1 to 3 between them. And for this experiment I've chosen these 4 resistors with sizes 270, 680, 2K and 20K, and the way that I'm going to construct ratio of 1/3 between them is as follows. So if I have my voltage source here and I parallel 2K with 20K, and then the voltage ratio between two additional resistors of 270 and 680 are as follows, then the output, which will be taken from here and the ground, is going to be 1/3 of the total input voltage, because 270 and 680 are in series and 2K and 20K are in parallel, and the summation of 270 plus 680 divided by 270 plus 680 plus parallel of 2K with 20K would be around 1/3 roughly. So that would be V out over V in, if you'd call it V in. This is the circuit that we're going to construct. Next, we make sure to provide a DC voltage of 3 volts to the circuit using this power supply. We need to make sure also that the current limit is high enough to allow enough current for the circuit. And over here we can verify the voltage level using a DMM, digital multimeter, to be around 3 volts. The circuit is hooked up as follows. So we have 680 ohms and 270 ohms in series, while 2K and 20K are in parallel. The circuit is hooked up as follows. The input comes at these two terminals, so the positive voltage goes to the input of this parallel resistors between 2K and 20K. Then it's followed by a series resistance of 680 ohms and 270 ohms that comes to the ground. In this breadboard, we typically consider the bottom blue line as the ground line, and also the output is going to be extracted from this node that connects these 680, 270 ohm series resistance with the rest of the circuit. So this node is the output, which is going to be connected to these two terminals and measured by a DMM. As you can see, the DMM shows 1.066 volts, which is around 1 volt, which corresponds pretty well with the ratio of 1 to 3 with respect to 3 volt input. Our analysis also represent the simulated or expected V out over V in to be around 0.34 based on the ratio of the resistances that we have chosen so far. And our measurement also proves that the output voltage of 1.066 divided by the input voltage of 3 points results in about the same value of 0.355. So these two match with each other. The next part that the lab is asking about is the current flowing through the output resistance, which in this case is a series of 680 and 270 ohms, and we call that as R2. And this current that is flowing from the output node down to the ground through this R2 is going to be measured. Before going into the measurement, we do a rough analysis of what it would mean in theory. So I would be the voltage difference between the resistance of R2 divided by the resistance R2, which in this case it would be V out minus 0 divided by R2. In our measurement, it turns out that V out is 1.066 and R2 is 950 ohms, and it should appear at about 1.1 milliamps. Measuring this value using the ammeter mode of this DMM, we get 1.13 milliamps. And the way that ammeter is located in and hooked up in the circuit is as follows. So now that we are using that instead of a voltage measurement device as a current measurement device, we need to put this in series with the rest of the circuit. So in a sense, these two wires are connected to the ammeter and are in series with this combination of the resistors and this series output resistance. So this combination of resistors comes to one end of this ammeter, and also the other end of ammeter is going to enter the output resistance. And this whole loop creates a single loop. The current flowing through this ammeter is again measured as 1.13 milliamps, which is close to the expected value. In the next part of the experiment, E2 is asked to design a sinusoidal waveform-based circuitry. So in this case, we have used this function generator to generate a frequency of 2 kilohertz with an amplitude of about 4 volt peak to peak that enters our circuitry instead of the DC input. The output waveform is being shown on the oscilloscope as shows. We can use cursors in order to find the maximum to the minimum or peak to peak values, and dip to dip or max to max in order to find the period or the frequency of operation. In this case, we'll use this bottom cursor. When we press this, we have the option of moving the cursor up and down using this knob, and also pressing this one more time. It can go both up and down, and also pressing it once more, actually it allows for the lower center line to move. If you want to actually switch between these horizontal lines to these vertical lines, we need to press this select button. Now we can move the vertical lines using this knob again, and also pressing it again allows us to move both together, and also pressing it again allows us to move only the left cursor alone. And in this case, the measurements on the left side show approximately the frequency of 2.03 kilohertz with a peak to peak value of about 3.96 volts. As shown again on the right side, the frequency is 2 kilohertz, which correctly is shown on the oscilloscope. So this is the input of the circuit that is shown on the oscilloscope. However, if you measure the output of the oscilloscope using this blue wire to the second channel of the oscilloscope, again connecting one end of the oscilloscope to the output in the other end to the ground, we can see channel 2 as well, that is shown with the blue color as well. So this blue line represents the output, which is shown with the blue color, and it is seen that it's roughly 1/3 of the output if you're considering the volt divisions. The next part of the experiment is asking about how to find the voltage across these two parallel resistors of 2K and 20K, or known as R1. In this case, it's not easily achievable using one of the channels of the oscilloscope, because either of the channels need access to the ground, which in this case none of these nodes are ground nodes, and therefore we cannot make use of a single channel of the oscilloscope to get to this voltage across R1. However, there is also another way to get that, and that is if one channel of the oscilloscope is responsible for V in and another channel is responsible for V out, then if we can subtract these two from each other, in that case we can get V in minus V out. We would be able to find the voltage across this parallel pair of resistors. In this case, we are going to engage the functionality of the oscilloscope called math here. So when we are engaging that, it allows us to use different combinations of mathematical arithmetic equations like summation, subtraction, multiplication, division, and stuff like that. So as soon as we choose subtraction, we can select this with this knob, This operation allows us to turn it on or off, but before that we need to choose the channels that are going to act as source A and source B. So in this case, our channel 1 represents the input, so we can designate that to be source A, and channel 2 is the output, so we can call it source B. And once A minus B is going to be calculated, essentially that gives us the result of the voltage across R1, as we discussed. So as soon as we hit the bottom operation on, you see that a new waveform is being generated that is somewhat between this yellow and the blue lines that represents the subtraction between the yellow and the blue one, or indeed the input and the output. We can also use the cursor, as we discussed before, to find the peak-to-peak value of this new curve for the R1. So in order to do that, we use the cursor button, and also we can select horizontal lines, and we can move each one of these lines up and down. The bottom line is done, so we can press it. So the top line is also activated, so we can move it down, and as soon as it's done, you can see that there is a BY minus AY that is shown here, which represents the peak-to-peak voltage across that. So it takes us to about 2.7 volts, 2.68 volts, which is about a 2/3 of 4-point peak-to-peak value. The next section of the experiment, E3, it's all about average powering, that we are going to make use of the DMM in order to get the average power AC of the circuit. So still we're using the function generator to get the frequency of 2 kilohertz of our circuitry as shown in the inputs. And in this case, we are going to measure the AC voltage using the DMM of the input and also the output of the circuit as well. So let's start from the input. So in this case, both inputs are going to be connected to these two ports of the DMM, and DMM is going to measure nothing but the RMS voltage of the input. So in this case, it shows 1.4 volts, which can be verified using these calculations. As you can see here, the input voltage RMS is nothing but the peak voltage divided by square root of 2, which in this case, as we have chosen that to have a peak voltage of 2 volts divided by square root of 2, we'll get square root of 2, which is about 1.4 volts, which is what we are seeing here. And at this moment, if I change the output, if I change the RMS voltage that it's going to read from the input to the output, now the output is going to be measured on the DMM as RMS, and it shows about 4.48, which again, if you verify with our assumption that the AC RMS value of the output is going to be the peak output divided by square root of 2. So since the output is about 1/3 of the input, so the peak output would be about 2.2 divided by 3 and divided by square root of 2. There is a typo here. It would take us to about 0.48 volts, which is the correct value as shown on the DMM. So the next part of the experiment is asking about the current in AC mode using DMM. So again, the current mode of the operation will be done when the DMM is in series with the rest of the circuitry to make a single loop. As you can see here, this combination of R1 resistors, these parallel resistors, are going to enter the blue wire going to the DMM, and the return path is going to be connected directly to R2. Now, everything in terms of R1, DMM, and R2, they are all in series with each other to make a single loop. And now, when we are going to measure the RMS value of the current using DMM, we need to make sure that these two first buttons are pressed in to make sure that the RMS value and also in AC mode are going to be measured, and also the milliamp button is going to be pressed in, and here we will choose the range of about 2, so that the value that we read is about 0.6. And since this all comes at the dimension of milliamp, so it will be 0.635 milliamps of the current. We can also verify that using our analysis, since the output RMS current is the same as output voltage RMS divided by R2, and since we have got the value of 0.48 as the output RMS voltage, we can divide that by R2, which is 950 ohms, and then we can get about 0.5 milliamps of the output current. So there is a little bit of change in values, but that might be the error of the experiment. However, the whole value would be in milliamps. The last part of the lab is discussing about finding the average and peak power at the output. As we discussed, this is a sinusoidal waveform that has a peak value and also an RMS value. But the average power is this multiplication of the RMS value of the voltage multiplied by the RMS value of the current. And as we have calculated and measured the RMS value of the voltage to be about 0.48 volts and the RMS value of the current to be about 0.5 milliamps, so the multiplication would result the value of 0.24 milliwatts of the average power. However, for the peak power of this sinusoidal waveform in the output, since the whole circuit is resistive, there is no phase difference between the voltage and the current. In this case, the output maximum occurs at the same time for both voltage and the current, and we just need to find what would be the maximum of the voltage and maximum of the output current and multiply them together to get to the maximum of the power at an instance of time. Maximum of the output, however, is square root of 2 times the RMS value of the voltage that we have measured using the DMM, and the maximum amount of current would be square root of RMS value of the current that we have measured using the DMM again. So in a sense, square root times square root becomes 2, and RMS value of voltage times RMS value of the current becomes the power average that we measured earlier. So in this case, the average power times 2 becomes 0.48 milliwatts as the peak power at an instance of time for R2.